We live on a small rocky world orbiting an ordinary star in an ordinary spiral galaxy. When we look up at the night sky, we see the past written in light. Starlight that has traveled for tens, hundreds, or millions of years across interstellar space before it reaches our eyes. Those pinpricks of light are reminders that space and time are intimately connected. They're also reminders that the universe has a story. Our story, the story of our sun, the story of our Milky Way, and the story of the cosmos are all entwined. When we ask what will happen at the moment the universe finally dies, we are actually asking what kind of story we are living in. Are we in an eternal, ever-expanding epic? Are we on a roller coaster that will climb and then plunge back into itself? Will the cosmos tear itself apart in a catastrophic burst? Or will it fade to black in endless silence? These questions are not just science fiction. They take us to the edge of what we know and into the realm of speculation, but they also force us to engage with some of the most beautiful and mind-bending concepts in physics. Dark energy, entropy, quantum vacuum decay, and the ultimate fate of matter itself. The known universe came into being about 13.8 billion years ago in an event we call the Big Bang. In those first fractions of a second, the fabric of space-time expanded from an unimaginably dense and hot state. Quantum fluctuations imprinted slight variations in density that over billions of years grew into the stars, galaxies, and cosmic structures we observe today. Thanks to observations of distant galaxies and the cosmic microwave background, we know that the expansion of space is not slowing down but speeding up. Measurements of galaxies' redshifts show that space itself is stretching. The more distant a galaxy, the faster it appears to recede. This accelerating expansion is attributed to a mysterious component of the cosmos we call dark energy. Dark energy makes up roughly 68% of the total energy density of the universe. Its nature is unknown, but it exerts a kind of anti-gravity on cosmic scales, pushing space-time apart. For decades, astronomers assumed this dark energy behaved like Einstein's cosmological constant, a fixed energy density of the vacuum that remains the same as space expands. In that scenario, the universe would expand forever, cooling and thinning out over unimaginable timescales. Stars would gradually exhaust their nuclear fuel. Galaxies would drift so far apart that they would no longer see each other. In the far future, the last generation of stars would be dim red dwarfs. After trillions of years, even those would extinguish, leaving behind white dwarf embers, neutron stars, and black holes. When we talk about the big freeze, or heat death of the universe, we imagine this scenario stretched to the extreme. In a perpetual expansion, all matter and energy become spread so thinly that no new structures can form. Energy dissipates, temperature differences vanish, and the universe approaches a state of maximum entropy, where nothing changes and no work can be done. This is a direct consequence of the second law of thermodynamics, which states that entropy, a measure of disorder, tends to increase over time in a closed system. If dark energy remains constant, the cosmic expansion ensures that matter and radiation will become ever more diffuse. Stellar remnants like white dwarfs, the compact cores of medium-sized stars, were once thought to be the longest-lived objects in the cosmos. They would slowly cool, the remaining nuclei decaying through quantum tunneling. Yet new calculations suggest these remnants won't last as long as once assumed. When physicists at Radboud University considered the effect of Hawking radiation on white dwarfs, a quantum process by which black holes emit tiny amounts of energy, they found that the same principle can cause white dwarfs to evaporate. According to their study, the last remnants of stars will perish in about 10 circumflex, 78 years. This is still a mind-boggling number, a 1 followed by 78 zeros. Yet it is dramatically shorter than earlier estimates that stretched into 10 circumflex 1100 years. In this far future, all stars will have died, leaving behind only black holes. Those black holes, in turn, will emit Hawking radiation and evaporate on timescales that depend on their mass. A black hole with the mass of our sun would take about 10 circumflex 67 years to disappear through this slow leak. Supermassive black holes, millions or billions of times the mass of the sun, would take even longer, but eventually they too would radiate away. The universe would become a thin, cold soup of photons, neutrinos, and particles barely above absolute zero. Time would still pass, but nothing meaningful would happen. The heat death scenario is sobering because it suggests a universe that never truly ends, but simply fades. Yet it also emerges naturally from our current understanding of cosmology. If dark energy is a constant, then the expansion of the universe will continue to accelerate indefinitely. Gravity will weaken in relative terms. Galaxies outside our local group will move beyond our cosmic horizon, the boundary beyond which light can no longer reach us. The night sky will empty out. Stars and planets will grow cold. Eventually, the only activity left will be the occasional quantum event. Protons decaying, electrons tunneling out of their atoms, or a solitary black hole giving off a whisper of radiation. After the last black hole evaporates, even quantum fields will settle into their lowest energy state. This is the universe as a dying ember, a cosmic winter with no spring. The scale of time involved is difficult to grasp. 10 to the power of 78 years is so long that if you were to write one digit every second, you would not finish until long after all the matter in the universe had dissolved into radiation. Yet compared to infinity, even 10 circumflex 78 years is finite. Eventually the big freeze would complete its task and the universe would reach thermodynamic equilibrium. However, not all models of the future point toward a cold, endless expansion. An intriguing alternative has been revived by recent observational data. The idea that dark energy may not be constant but may change over time. At the heart of this discussion is the cosmological constant lambda, which Einstein originally introduced into his equations of general relativity to allow for a static universe. After Edwin Hubble discovered that the universe is expanding, Einstein reportedly called the constant his greatest blunder. Yet the concept returned when astronomers found in the late 1990s that the cosmic expansion is accelerating. In most models, lambda is assumed to be positive, giving rise to a repulsive force. But what if lambda is slightly negative? The Dark Energy Survey and the Dark Energy Spectroscopic Instrument have mapped millions of galaxies, measuring their distribution and the expansion rate of the universe. A theoretical study using this data, led by physicist Henry Tai, proposes that dark energy might involve a low-mass particle field that behaves like a cosmological constant early in cosmic history, but then evolves. In their model, this axion-like field causes the effective cosmological constant to become negative. When lambda turns negative, gravity eventually overcomes the expansion. The universe would expand for roughly another 11 billion years, reach a maximum size, and then begin to contract. This contraction would not be immediate. It would be gradual, like a brake slowly engaging on an enormous cosmic machine. After an additional 8 billion years of shrinking, all matter and energy would collapse into a dense state, a big crunch. In this scenario, our universe would have a total lifespan of about 33.3 billion years. We would currently be living just past the halfway mark. Gravity would ultimately draw galaxies back together. Temperatures and densities would rise. As the universe contracted, the cosmic microwave background would blue shift, heating up. Stars and planets would be torn apart by tidal forces, long before the final singularity. At the moment of the big crunch, space and time as we know them would cease. Whether that final collapse would lead to a new Big Bang, a so-called Big Bounce, is a question that theory cannot yet answer. Our current physics breaks down at such extreme densities where quantum gravity effects become significant. The Big Crunch scenario reminds us that the cosmos might be cyclical, a phoenix rising from its own ashes. It suggests that cosmic history could be punctuated by recurring births and deaths, each perhaps erasing the memory of the previous universe while seeding conditions for the next. Another possible fate for the cosmos arises if dark energy is not just a constant but increases in strength. When astronomers talk about the equation of state of dark energy, they refer to the ratio of its pressure to its energy density. If this ratio is less than 1, we enter the realm of phantom energy. In that case, the repulsive force driving the expansion of the universe would grow over time. The result is the so-called Big Rip. In this scenario, everything from galaxies to atoms is ultimately torn apart. As the cosmic acceleration increases, gravitationally bound systems begin to fail. First, galaxy clusters fall apart. Then, the Milky Way itself would be shredded. Later, the solar system's planets would be ripped from their orbits around the sun. Stars and planets would be torn apart by tidal forces. In the final minutes before the end, even the molecular bonds that hold matter together would be overcome. Space itself would rip, and the fabric of space-time would be torn. Estimates based on current measurements suggest that if phantom energy exists, the Big Rip could occur roughly 22 billion years from now. From the perspective of a galaxy dweller, The last days of the universe would be a terrifying sequence. Luminous objects disappearing beyond the cosmic horizon, gravitational systems dissolving, and eventually matter itself fragmenting into its constituent particles. The Big Rip is speculative because observational data currently indicate that the equation of state of dark energy is close to 1, consistent with a cosmological constant. Yet the possibility reminds us that our understanding of cosmic acceleration is incomplete. It underscores how sensitive the fate of the universe is to the properties of dark energy, a substance we have yet to comprehend. Then there is the Big Slurp, sometimes called vacuum decay. This scenario doesn't arise from cosmic expansion, but from quantum field theory. In quantum physics, every particle is associated with a field that permeates space. The Higgs field, for instance, gives particles their mass. According to current measurements, the Higgs field may be in a metastable state, a local minimum rather than the global minimum of its potential energy. That means there exists a true vacuum state at a lower energy. Quantum tunneling could, in principle, cause a tiny region of space to fall into this true vacuum. This bubble of true vacuum would then expand at nearly the speed of light, reconfiguring the laws of physics as it went. The energy difference between our false vacuum and the true vacuum would be released in a flash, destroying everything in its path. In this vacuum decay, the universe would essentially reboot itself into a new configuration, with different constants and perhaps different physics. Thankfully, calculations suggest the probability of such an event in our universe is extremely small. Perhaps one event in 10 circumflex 100 years. Given that the universe is only 13.8 billion years old, a lifetime of 10 circumflex 100 years is unimaginably long. The Big Slurp is therefore more of a theoretical curiosity than an imminent threat. Yet it serves as a profound reminder that the ground beneath our reality is not necessarily as stable as we assume. It highlights the deep connection between cosmology and particle physics. The fate of galaxies may be tied to the properties of tiny particles like the Higgs boson. It's worth acknowledging that these scenarios are not mutually exclusive. The cosmos could end in a big freeze or a big crunch, depending on the behavior of dark energy. It could be torn apart by a big rip if phantom energy dominates. A Big Slurp remains a remote but fundamental possibility. There are even more speculative models, cyclic universes that oscillate endlessly, Big Bounce scenarios where a contracting universe rebounds into expansion, ekpyrotic models where colliding branes in higher dimensions drive cosmic cycles and heat death plus quantum revival ideas, where after an exceedingly long dark era, rare quantum fluctuations spawn new universes. Cosmology is full of creative thinking because the data we have are limited by the finite speed of light and the finite age of the cosmos. We infer the fate of the universe from the redshift of distant galaxies, the cosmic microwave background, the distribution of matter, and the properties of dark energy. Modern projects such as the European Euclid Space Telescope, NASA's FAREX mission, and the Vera C. Rubin Observatory will provide more detailed maps of cosmic structure and expansion. These observations may confirm or refute the hints that dark energy is evolving. If they show that the equation of state of dark energy differs from once our expectations for the far future, would shift, the cosmic future is thus an active area of research, even though its outcomes will play out on timescales far beyond human existence. Now let us focus on the concept of entropy and the arrow of time. Thermodynamics tells us that the total entropy of a closed system tends to increase. The universe is, as far as we can tell, a closed system. In the early universe, matter and energy were concentrated in a hot, uniform state with low entropy. As the universe expanded and cooled, structure formed: stars, planets, and life. This organization comes at the expense of increased entropy in the environment. As stars fuse hydrogen into heavier elements, they radiate energy into space. This radiation, when absorbed and re-emitted by interstellar gas or cosmic dust, eventually ends up as low-grade thermal energy. Over trillions of years, the amount of usable energy available to do work declines. The Big Freeze represents the ultimate extrapolation of the second law. In contrast, a Big Crunch would seem to reverse this trend, compressing everything back into a high-energy state. Yet a contracting universe also raises entropy as gravitational clumping increases and processes within stars and black holes continue to generate heat. In either scenario, the arrow of time, the direction from low entropy to high entropy, persists. Even if a bounce occurs, resetting cosmic expansion, the new universe would start from a state of high entropy inherited from its parent. This challenge known as the entropy problem, is one reason some physicists are skeptical of cyclic cosmologies. For a cyclic universe to avoid a buildup of entropy across cycles, some mechanism must reset or dissipate entropy, perhaps through extra dimensions or exotic physics. When we talk about Hawking radiation and the evaporation of black holes, we are dealing with a quantum effect that arises at the event horizon. Stephen Hawking showed in the 1970s that black holes are not entirely black. They emit radiation due to quantum fluctuations in the vacuum near the horizon. One particle of a particle-antiparticle pair falls into the black hole while the other escapes, carrying away energy. This causes the black hole to lose mass. Small black holes radiate more strongly and evaporate faster. Larger ones are colder and last longer. For a stellar mass black hole, the evaporation time is roughly 10 circumflex 67 years. For supermassive black holes, it may be 10 circumflex 100 years or more. When a black hole evaporates, it leaves behind a faint burst of energy. The final stages of evaporation could be energetic, but by then there'll be little else in the universe to absorb that energy. The evaporation of black holes is one of the key processes that drive the universe towards the big freeze. As long as black holes exist, there is a reservoir of low entropy matter locked away. When they radiate away, that reservoir is lost and entropy increases. White dwarfs and neutron stars, which are supported by quantum degeneracy pressure, will not collapse into black holes if they are below certain mass thresholds. They will instead cool and crystallize. But even these remnants are subject to quantum effects. Physicists have shown that white dwarfs can eventually decay via quantum tunneling of electrons. Incorporating Hawking radiation into this calculation leads to the conclusion that white dwarfs might decay after about 10 circumflex 78 years. This sets an upper limit on how long any stellar remnant can persist in a big freeze scenario. After these times, there will be no stars, no planets, no black holes, and no chance for new structure to emerge. The cosmic timeline of our universe can thus be divided into eras. We are currently in the stelliferous era, when stars shine and galaxies thrive. This era began about 100 million years after the Big Bang and will continue for several trillion years. After that comes the degenerate era, when star formation ceases and existing stars slowly die out. Brown dwarfs, white dwarfs, neutron stars, and black holes dominate. Planets may continue to orbit these remnants, but they will be dark and cold. In the far future, gravitational interactions may fling planets out of their orbits, leaving them to wander the interstellar void. The degenerate era transitions into the black hole era once most objects have become black holes. This period could last up to 10 circumflex 100 years. The final phase is the dark era, when all black holes have evaporated and the universe is a thin soup of particles. At this stage, physical processes take place on timescales so long that meaningful events become rare. Quantum fluctuations might occasionally produce small black holes or new Big Bang-like events, but the probability is incredibly low. Some cosmologists even speculate that in an infinite time frame, random fluctuations could generate Boltzmann brains, self-aware entities arising from chance arrangements of particles. While such ideas are whimsical, they illustrate how the laws of physics allow for bizarre phenomena given enough time and space. Yet these phenomena do not offer a reprieve from the overall decay. The overarching trend in the big freeze scenario is toward uniformity and emptiness. From a human perspective, these timescales are almost impossible to relate to. Our entire species has existed for a few 100,000 years. Civilization, as we know it, has been around for perhaps 10,000 years. The oldest living structures on Earth, such as long-lived trees, are only thousands of years old. We measure our lives in decades. Even the lifetime of the sun, about 10 billion years, is beyond direct human experience. Yet cosmology asks us to envision trillions, quadrillions, or even 10 circumflex 78 years. Doing so provides a humbling perspective. It also highlights the beauty of a universe that evolves on scales far beyond our lives. To conceive of the moment the universe dies is to imagine a farewell that occurs in the deep future, long after any observers like us are gone. That does not make the question irrelevant. On the contrary, it forces us to confront what we value in the present. Knowing that the cosmos may have an end, we might appreciate more deeply the finite and precious time we have. Let us return to the Big Crunch scenario for a moment. A collapsing universe is not necessarily a disaster from a narrative standpoint. If the cosmos contracts, it could compress cosmic background photons raising the temperature again. Galaxies would merge, gas clouds would fall together, and new bouts of star formation might occur, briefly as the cosmos heats up. However, as densities increase, everything would eventually be torn apart. Structures would be destroyed, and near the end, conditions would become similar to those at the beginning of the universe. At the final instant, the gravitational tidal forces would crush atoms, nuclei, and subatomic particles. Does the universe bounce at this point? Some models in string theory and loop quantum gravity suggest that a bounce is possible. Quantum gravitational effects could prevent the formation of a singularity and cause the universe to re-expand. In the Big Bounce, our universe would be one cycle in an infinite series. Each cycle would start with low entropy because the previous universe's high entropy is smeared out or restructured by exotic physics. The details remain speculative, but the Big Crunch scenario emphasizes a key point. The ultimate fate of the universe depends critically on the sign and evolution of the cosmological constant. A tiny change in the value of dark energy could alter cosmic destiny from freeze to crunch or vice versa. Our best observations continue to favor a positive, near-constant dark energy density, but the new data hint that it might be slightly different. Upcoming experiments will reduce uncertainty. If they confirm a negative or time-varying cosmological constant, then the Big Crunch might not be science fiction. The Big Rip is no less dramatic. In this scenario, as the cosmic acceleration increases, the Hubble radius, the distance at which objects recede faster than the speed of light due to the expansion of space, shrinks. That means that more and more of the universe becomes causally disconnected from a given observer. For an observer in the Milky Way, the cosmic horizon would move inward. Eventually, the horizon would swallow the Milky Way, then the solar system, then Earth. A few months or weeks before the final moment, molecules would be torn apart. Atoms would be ripped into nuclei and electrons, nuclei into protons and neutrons, and those into quarks. Finally, even space-time itself would break apart. Although this sounds like science fiction, it is grounded in the mathematics of general relativity, when the equation of state of dark energy is less than 1. Observationally, current constraints allow such values but prefer one within a small error. So the Big Rip is unlikely given current data but cannot yet be ruled out. The timescale of 22 billion years is interesting because it is comparable to the timescales of the Big Crunch predictions. That means our cosmological future could be violent or silent, depending on the properties of something we cannot see but can measure indirectly. The Big Slurp, while unlikely, raises philosophical questions about stability. It suggests that the laws of physics themselves may be metastable. The constants we measure, such as the mass of the Higgs boson or the strength of the weak nuclear force, may not be fixed by necessity but by circumstance. Our universe might be perched in a local energy minimum that looks stable on timescales far longer than its current age. Yet there could exist a deeper minimum that, if reached, would cause a phase transition. In everyday life, we experience phase transitions when water freezes or boils. In cosmology, a vacuum phase transition would change the basic interactions that govern matter. Such an event would propagate at nearly the speed of light, leaving no warning. It would not be a consequence of cosmic expansion, but of quantum instability. The fact that this possibility exists in our theories is both unsettling and inspiring. It reminds us that the fabric of reality is far richer than our daily experience suggests. And the fact that calculations estimate the probability of such a transition at roughly one event every 10 circumflex 100 years gives us comfort that it is exceedingly improbable. As we consider these cosmic fates, we might ask, why dwell on such distant speculative events? One answer is that exploring the universe's end teaches us about its beginning and present. To understand whether the cosmos will freeze, crunch, rip, or slurp, we must measure dark energy, dark matter, and the curvature of space with exquisite precision. These measurements inform not only cosmology, but also particle physics and gravity. They challenge us to unify quantum mechanics and general relativity. They drive the development of new telescopes, satellites, and particle colliders. Another answer is that thinking about the universe's fate brings a sense of perspective. It highlights the fragility and rarity of the conditions that allow life to exist. It emphasizes that the cosmic stage on which we play our small drama is dynamic. When Neil deGrasse Tyson speaks about the cosmos, he often emphasizes how knowledge of our cosmic origins enriches us. Understanding the universe's potential demise does the same. It reminds us that we are part of a story that spans 13.8 billion years, and that may continue for billions, trillions, or 10 circumflex 78 years more. It underscores the imperative to explore, learn, and appreciate. We should also recognize that our knowledge is provisional. New data could transform our understanding of cosmic fate. The discovery of dark energy itself in the late 20th century was a shock. It overturned the expectation that cosmic expansion would slow. Similarly, the realization that the cosmological constant might be slightly negative has prompted discussions about a possible future collapse. The next generation of instruments will measure the expansion rate and dark energy equation of state to greater accuracy. They will map the large-scale distribution of galaxies, search for deviations from general relativity, and test the standard model of cosmology. Laboratory experiments may detect particles that contribute to dark energy or dark matter. The future circular collider planned by CERN will probe the Higgs boson and other particles with unprecedented precision. By narrowing the range of possible physical constants, we will better constrain the probability of vacuum decay. In short, the story of the universe's end is part of ongoing scientific inquiry. It is not just a philosophical question, but a driver of empirical research. In the far future, when the last stars have died, there may be no observers left to witness the universe's final moments. Yet our minds, here and now, can project our imagination across cosmic time. We can picture the last white dwarf, slowly radiating away energy until it vanishes. We can envisage galaxies rushing beyond the cosmic horizon, leaving behind a lonely Milky Way. We can imagine a contracting cosmos heating up as it collapses, or a universe torn apart at every scale. They are part of a tradition of cosmological storytelling that stretches back to ancient myths and continues through modern science. Today, our stories are informed by mathematics, observations, and physical laws. They are also enriched by our sense of wonder. The moment the universe dies may be unimaginably distant, but thinking about it shakes how we appreciate the universe while it lives. Ultimately, whether the universe ends in a cold, dark fade, a catastrophic collapse, a violent tear, or a quantum reboot, the cosmos has already given us something extraordinary: the capacity to contemplate its fate. That capacity is a product of billions of years of cosmic evolution. It arose through the synthesis of heavy elements in stars, the formation of planets, the emergence of life, and the evolution of brains capable of abstract thought. When we gaze at the night sky and ask about the end of everything, we're expressing a curiosity that is itself a triumph of cosmic history. The atoms in our bodies were forged in long-dead stars. The photons that strike our retinas have traveled across expanses of space and time. Our questions about the universe's future are an extension of its past. In this sense, the moment the universe dies is not just an event in the distant future. It is a reflection of our relationship with the cosmos. It reminds us that our existence is both fleeting and connected to the deepest workings of reality. So as we ponder the different endings, freeze, crunch, rip, or slurp, let us also celebrate the fact that we can ask, and let us commit to using our brief moment in cosmic time to explore, understand, and cherish the universe that made us.